okay? So the first term is how much of Earth is covered with large bodies of water. The answer is in red there, 70%. Actually, it's a multiple choice question, okay? The next one, with regard to water, how is it distributed? Where is it? And I kind of circled a couple things there. The first circle here is oceans have by far the most amount of water, okay? And then actually of that little sliver, which is kind of what we call fresh water, most of it is glaciers. Phase changes, we talked about that, okay? And then here's a little figure from, I don't think it's from, this might be from your textbook. Basically, as you go from a gas to a liquid to a solid, energy is released, okay? As you go from a solid to a liquid or liquid to a gas, energy is absorbed. The hydrological cycle, otherwise known as the water cycle, I just kind of brought that figure in from your textbook, the whole kind of evaporate, clouds, rain, evaporate, clouds, rain. Okay, hydrological cycle. Saturation temperature table. Okay, so first off, what is saturation? Now, you guys are probably familiar with the whole 100% relative humidity. 100% relative humidity. The air is saturated. That means that at that temperature, it cannot hold any more water. That's what saturation is. And then, and I'm showing you this little box right here. This little box with the cute little water molecules. Saturation is when actually the amount of water that's evaporating is equal to the amount of water that's condensing. That's what saturation is. The other table is the old adage where we say warm air, let's see, how's that go? Warm air holds more water vapor than cold air, okay? So I have an arrow going decreasing temperature as it gets cold. Notice that it can't hold as much water, okay? So as you go up in this table, okay, it's hard to read, but again, these figures are also in your notes, you know. If we pick on, looks like 15, you see this 15 here? That's the temperature, 15 Fahrenheit. It can hold 10 grams and be saturated. 10 grams of water in 1 kilogram of dry air. That's what that means. So cold air holds less water. So there is going to be a question on there about calculating percent relative humidity. Percent relative humidity. So percent RH. So 100% relative humidity, saturation, right? Well, what if you're not at saturation? When you look on the Weather Channel, say, what is the humidity out there? Well, the AC is for the actual amount of water, and the MC is what you get from the table. That's the maximum amount that the air can hold at that temperature. Okay? So I brought in a figure from your textbook. Remember, we kind of had we had like 2 or 3, I think maybe 2 slides that had these cute little flasks, flat bottom flasks in there. This particular example, we have 100 grams of air in there. It's containing 7 grams of water vapor. Notice they tell you what the temperature is. It's 20 degrees Celsius. So basically what you do is you find 20 degrees Celsius on here. Okay, to me it's looking like, it's hard to tell, but I'm kind of thinking here, 20 degrees Celsius on here. Okay, that means at 20 degrees Celsius it can hold 14 grams. And then you look at it one more time and it says, oh, I don't have 14, I have 7. So what is the percent relative humidity? It's what you have, your AC, 7, divided by what it can hold, which is 14. 7 divided by 14 is 50%. Half. Okay, so that's kind of how that works. The next one, a heat index table. There's several tables and several figures on this test. So remember, there's 2 feels-like temperatures, and one is in the summer, and this is in the summertime. So along the top there, actually you see what your thermometer temperature is, and then along the side there is what the percent humidity is. So I just kind of picked, for example, what if I told you my thermometer says 89, and I said my percent humidity is 60%. What's the feels-like temperature? And that's 91 right there. That's how those go. You see what the thermometer says, okay? And then you see what your relative humidity is and where they intersect. That's your feels-like temperature. And then why are clouds white? Because light is scattering. Light from the sun is scattering. Now, how is it scattering? It's scattering on L and G. Of course, that stands for, oops, I should have said solid. I should say liquid and solid. Okay, why are your clouds milky white? I've been saying it's because actually water has condensed. You have liquid water up there. But if you have solid snowflakes, you'll also get that scattering. The next one, how come we get sleet and freezing rain? And we get sleet and freezing rain for the same reason. And I just kind of pulled sleet in here. Why do you get sleet or freezing rain? Well, probably what falls as snow melts and then it refreezes. So I put cold, warm, cold here. So basically the reason you get, you can look at a couple different ways. You can say, well, a warm layer has inserted itself above a cold layer, or you could say a cold layer has inserted itself underneath a warm layer. However you want to say that. But sleet and freezing rain come from the same conditions. The next one, I just love the word bergeron. Okay, bergeron is what had happened today to give us our pretty little snow. Okay, the bergeron process, if anybody says in meteorology, they're like, oh, that's the bergeron process going on. It's just creating snow. 10 cloud types. Okay, so I just kind of brought the figure in from your textbook. I can't remember, did you guys have a homework for 10 cloud types? No, okay. So know the 10 cloud types. Now, remember that when you review this, you're going to see that clouds are based upon whether they're low clouds, this is low, whether they're middle, or whether they're high clouds. Okay, remember if they're low, if they're middle, they use alto, if they're high, they use cirro. Okay, might want to take a look at all that. So 10 cloud types. Precipitating has NIMB or NIM. Fog. I just brought something in from your notes. Down here is the fog. Okay, remember there's 4 types of fog. But the thing about fog is it's milky white. Why? Because its water's a liquid. Okay, so basically fog is a cloud at ground level. There's different ways to create fog. One of my favorite ways, hint, is that first one, radiation fog. That's the one where you get up in the morning and you see the fog. Basically, radiation fog is created because the earth cooled down overnight. And then the last one, I don't think I have anything for it. If you were here for lab, actually, do you guys remember when we took those 2 thermometers? We didn't sling around. When you took the 2 thermometers and you used a fan, you wetted one and one was dry, those 2 thermometers, and then you used that table. Basically, when you wetted one and one was dry, one got cooler and one was warmer, and then you subtracted, you came up with the difference between the cold and the warm one. Okay, and then you used a table, actually, so that's worth some extra credit points in the test. So if you have that, you can take a look at it. Okay, equals lab. All right, air masses. There are 6 types. I kind of usually think 5 types of air masses, but so there's the air mass types. Remember, they're indicated by whether they're dry continental or moist maritime, and whether they're cold polar or warm tropical, or if they're very cold, they're Arctic. Okay. Air mass source regions are right here. Air mass source regions. Basically, if this is us right here, how do we get a warm, moist air mass? Well, they come from right here. Okay. How do we get a dry, warm air mass? Well, it comes from right here. How do we get a cold, moist air mass? They come from here. Or how do we get a really cold, moist air mass here? And then how do we get a cold, dry air mass, Canada? Okay. So, one air mass only forms in the summertime. That's this one. Okay. One air mass only forms in the wintertime. And actually that is the maritime Arctic, which isn't shown here. So source regions, where a chunk of air hangs out for a while to pick up being warm or cold or dry or moist. Okay, so weather fronts. Weather fronts are where two air masses meet. Okay, and there are four types of weather fronts. There's a warm front, a cold front, stationary front, and a fluid front. And just today, we looked on the weather map and we saw that blue line with the triangles, cold front. Today we saw an alternating red, blue line. That's a stationary front. Warm front would have been red with semicircles. And a fluid front is usually purple. We did see one of those today, didn't we? So what's the difference between a cold front and a warm front? What sort of weather would you expect to see? Cold fronts are notorious for bringing storms, okay, and intense precipitation. Warm fronts are usually your precipitation lasts longer because of the overrunning that we talked about. All right, on to the next part. So that little pie diagram, the orange there, or kind of the tan color, that's all nitrogen. So most of the air we're breathing right now is nitrogen. It's usually, they say 80-20, 80% nitrogen, about 20% oxygen, followed by argon and some other miscellaneous things. Okay. There are 3 gases that vary in our atmosphere. One of them is the water vapor, because you know humidity varies, so water vapor varies, right? Another one is carbon dioxide varies in our atmosphere, and the other one is ozone varies in our atmosphere. Why are the skies blue? And I don't have it on your test called Rayleigh scattering, but because it's the scientific term is Rayleigh scattering. But on your test, I'm pulling from you, why are the skies blue? And I like this figure. I think this is from your textbook, where basically you see the sun shining in the distance and kind of see the blue light kind of being what we call scattered. Okay, what the reason it's scattered is because that particular color from the sun basically interacts with the gases in our atmosphere. The next one, ozone. The formula for ozone is O3, like you see above. It's a variable gas. Ozone, and on the test I'm just asking about the good ozone. So the good ozone is in the stratosphere, and the good ozone protects us from that radiation from the sun, UV radiation. UV, that's an energy from the sun. Variations in carbon dioxide, there are 2 variations, okay? And both variations actually are shown on this figure over here. The kind of top part, what I put a squiggle, okay, I tried to kind of blow up the variation. That squiggle is each year the carbon dioxide varies. And the reason each year the carbon dioxide varies is because of photosynthesis, because plants doing their thing. One of the things you guys learned a long time ago is plants are great for sucking in carbon dioxide and spitting back oxygen. The other kind of trend from year to year to year to year actually is because of carbon dioxide is increasing the Earth's atmosphere, whether you want to say it's warming the Earth, which it is, or not, because of burning fossil fuels and deforestation. Greenhouse effect, greenhouse gases. So here's your greenhouse, okay? Basically, we talked about the reason we talk about gases in the atmosphere creating a greenhouse effect. What this is trying to show you is light is coming in, which is fine. It goes right past the greenhouse gases. It interacts with the Earth's atmosphere, and it heats up the Earth. And then this thing right here is heat. The red thing is heat. So basically what happens is that these same gases that let light in don't let heat out. That's why they're called greenhouse gases, greenhouse effect. Layers of the Earth's atmosphere. There are 4 main layers. The bottom one is the troposphere, then the stratosphere, then the mesosphere, and then the thermosphere. And one of the things you need to know is how does temperature change as you go up in each one of these. And so this figure does it. I put a C for cold, H for hot, okay? So basically it gets colder as you go up in the troposphere. It gets hotter as you go up in the stratosphere. It gets colder as you go up in the mesosphere, and it gets hotter as you go up in the thermosphere. So it kind of alternates like that. Okay, pressure of the atmosphere. So I chose just to bring in this little kind of, this is like a wedge of the Earth's atmosphere where these are gas particles, and the Earth's atmosphere is very dense down here and it's sparser up here. So up here we have, it's thinner, okay, less dense, and we have a lower pressure. Down here it's more packed, it's denser, and we have a higher. Okay. On to the next one. All right, so how do you get, like, you know, on the weather map we looked at just a little bit ago, we had an H for high pressure and an L for low pressure. How does that happen? And so we talked about how do you get horizontally a difference in pressures. One is, the first one is temperature. So actually the blue is cold, okay, and the red is hot. In general, cold temperatures bring high pressures, and warm temperatures, because they heat them up, the things go fast, actually bring low pressures. Temperature is the first one, moisture is the second one, and whether the air is moving or not is the third way. So we talked about those ways of getting pressure differences. Isobars are kind of like we saw on the weather map a little bit ago. Those are, a lot of times on a weather map you'll see these kind of lines, and those are probably isobars, and they are showing locations with the same pressure. So if it's a good map, I think it actually has what the pressure is, like the one we looked at. It said that it was like what the pressure was. So isobars are what we call contour lines, marking locations with the same pressure. So how is wind created? It's created, here's a figure that basically, because you have a high, an H over here, you have an L over here, and basically air wants to relocate from a high to a low. That creates wind. And we talked about the Coriolis force. And the Coriolis force is created because the Earth is spinning on its axis. So remember this little globe right here. What you're doing is you're looking at the North Pole down. Of course, the Earth is spinning counterclockwise, looking at the North Pole. And so if you were to, like, leave the Earth's surface and try to, in the air, and try to head towards the equator, actually the Earth would spin underneath you, and you would actually look like you're being deflected to the right. Okay, so that's kind of what the Coriolis force is. Anticyclones and cyclones, I kind of have the color thing going on here. I have purple for anticyclones, I have blue for cyclones. Anytime you see an H, that on the weather map, like we saw a little bit ago, that is an anticyclone. And H's generally bring kind of warmer surface temperatures. High or anticyclones oftentimes do have clear skies, and if there is some movement, it will be going clockwise around an H. Cyclones are your central low. Because the air is diverging there, oftentimes it's cloudy and rainy, and air will be going counterclockwise there. Then we talked about different scales of wind. So my check marks there, I know it's hard for you to see, but the first check mark is the smallest scale, that's microscale. And then the next one is mesoscale, or middle mesoscale. And the last one is planetary scale, or macro scale. So sizes of winds. Remember, the really small ones don't last very long. The big ones, the macro scale or the planetary scale, they last long. So I can't remember what this question is. I put it on your review sheet. It must be something on your test. But we talked about a few of those kind of mesoscale, middle scale winds. And the lake breeze in Chicago actually is an example of a mesoscale wind. And the reason we get a lake breeze is because Lake Michigan actually is kind of delayed in how it heats up. The land heats up faster than the ocean or the Great Lake, and so you end up with an incoming breeze. The next one, actually, you guys had a homework where it didn't look like this, but something like this. Know the cells, like you have the Hadley cell, the Ferrel cell, the polar cell in both hemispheres. And then know the different winds. So like here, if we just pick on the northern hemisphere, here we have the northeast trades, here we have the westerlies, and here we have the polar easterlies. So you'll do great on the test. The other thing to know in this figure is, do you know where the intertropical convergence zone is? And that actually is between the hemispheres, it's between the two Hadley cells. So that's kind of your hot spot. Remember, it moves a little bit throughout the year. It's not always at the equator, but that's the intertropical convergence zone, just under the Hadley cell in the northern hemisphere. Hurricanes. We call them hurricanes, but really more generically, it's a tropical cyclone. And depending upon where you're at in the world, you call them different things. The deadliest hurricane is the one in Texas, the Galveston hurricane. So remember, we haven't always named them. I didn't mention this in lecture, but we haven't always given them alternating male, female names. We used to just give them all female names. I think I mentioned that till somebody complained. But back in the 1900s, we just named them after the town that was hit. Ingredients you need to form a hurricane. There are 3 basically. You need nice toasty warm water. The second one is you need to be, you can't be too close to the equator because then you won't get spin going on. So you have to be actually on the other side at 5 degrees from the equator. And you need to have an unstable atmosphere. You need to have you need to have warm air rising. There's a question about naming hurricanes, or tropical storms actually. How do you name them? And I kind of brought in the what we talked about in lecture about naming them. Storm surge. Storm surge is just associated with landfall. Actually, specifically, it's the landfall of the eye. Okay, we have the most intense winds at the eye. Okay, and basically, when this thing moves this way, as it's projected here, when the eye hits land, and I kind of said it's like you're in a swimming pool and you go. Okay, so actually, it's going counterclockwise, and it's going to spin that water up onto the land. That's called storm surge. Spin. Then the last one, what forms hail? Hail is different than sleet and freezing rain. That's one of the things I kind of want you to know. Hail you'll only get as part of a thunderstorm, and that's being shown there. Hail is basically where something we call a grapple kind of goes down and up and down and up. It kind of catches the updraft and it gets larger, gravity kicks in, it falls down. It catches a stronger updraft, gravity, it gets larger, falls down. Stages of a thunderstorm cell, there are 3. There's the cumulus stage, the mature stage, and the dissipating stage. I think that probably do it for you. Features of a thunderstorm cell, that was a homework. Okay. Now, one of the things I don't think I emphasized in, I don't know how much I emphasized, but remember the overshooting tops? I just think those are so cool. Those are when it's gone above the tropopause into the stratosphere. There's the anvil you see over here. We have your updraft and your downdraft. This is your shelf cloud, okay, and here's your dust cloud. All right, types of lightning. And then I just decided to bring in pictures. The 80% actually is cloud to cloud, otherwise known as sheet, as in S-H-E-E-T lightning. Okay, and the bottom one is cloud to ground or ground to cloud. Okay, and it's at only 20% of lightning. So if you're going to get struck, it's going to be that kind of minority of the lightning. And the last one, heat lightning. Heat lightning is the lightning that you see but you don't hear because it's too far away. I think it's like 12 or 15 miles away. Basically, the sound dies before it gets to you. So all sorts of good stuff. All right. Any questions?